This is video 36 of Tensor Calculus. In this video, we're going to analyze a number of important properties of the covariant derivative. The first property we want to look at is what is often referred to as the sum rule. Here we have two tensors, P and Q. They both have the same index structure. They've got I as a contravariant index and J as a covariant index. So the index structures are consistent and they're both multiplied by scalar factors, so we know that when we add them together, this is a valid tensor. So what's it like to take the covariant derivative of such an expression? Well, we just go through the rules. First, we'll find the partial derivative with respect to zk of our expression as it is, 2pij plus 5qij. Then we're going to need two terms, one for each of the two indexes. The upper index is going to require a positive term, so we'll have gamma times our expression, 2p plus 5q. Here we're dealing with the I index, so j stays the same as it is. I is going to be a contraction here, so we're going to have km and I up here. Then we need a negative term to deal with the j component, so it's negative gamma times 2p plus 5q. This time I remains the same, and the lower index is going to be our dummy index, our contraction, and down here is kj. So there's the expression for the covariant derivative of that sum. Now what we're going to do is just to distribute each of these things. These last two terms are simply algebraic expressions, so we can use the distributive property. And the partial derivative is distributive, so we'll just expand these terms out individually now. Now what we'll do is to group this term, and this term together. And we can do the same thing for this term, and this term. Well, now I expect you see what's happening. This expression is just the covariant derivative of pij, and this is the covariant derivative of qij. Thus, our final result is as follows. So the sum rule is that the covariant derivative of a sum of tensors like this is equal to the sum of the covariant derivatives of each of those two tensors taken individually. Now, because we can factor out the scalar factor like this, we can also say that the covariant derivative is a linear operation. And finally, let me add a couple of comments that are probably reasonably obvious. The first is that although we have chosen an example with a second-ranked tensor, mixed tensor like this, that's only an illustration. The principle of the sum rule works regardless of the rank of the tensor or the index structure, as long as the index structure is consistent across the board. And the second thing is that I think you can see as well that if we had more terms, if we had another term here, then the principle extends to those extra terms over here as well. The sum rule works for any number of terms within the parentheses. If we had 5 terms here, then we'd have 5 terms on this side. Okay, that's all we'll say about the sum rule. Let's move on. Back in video 34, we introduced the product rule, but that analysis was limited to simple vector components. What I want to do today is to show you that the product rule works for tensors of any rank. So with this example, we have a second-ranked tensor multiplied by a third-ranked tensor. Now the claim is that if we apply the product rule here, we'll get the same result as if we take the covariant derivative of this expression directly. So the product rule would be that we first take the covariant derivative of the first factor, like so, multiply by the second factor, then multiply the first factor times the covariant derivative of our second factor. So let's see if that works. We'll proceed to expand each of these expressions out to their full expressions for the covariant derivative. So this expression is the covariant derivative of Sij. You can see the partial derivative. We have a contraction for the I index going this way and a contraction for the J index going in this direction. And then this expression is the covariant derivative of T RSI. We've got the partial derivative. We have a contraction for the R index, contraction for the S index, and a contraction for the I index, like so. Well, the next step is simply to expand the terms out. So all I've done is to take this term and distribute it here, here, and here. And I've taken this term and distributed it here, 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 and down here. So now take a look at this term and this one, and notice that if we rename m to I and I to m in this term, these two terms will be exactly the same except they're opposite in sign, so they will cancel each other out. And the reason that happens is because we have a contraction going on with index I here. All right, and also notice that these two terms together, this one added to this one, is simply what we'd have if we took the partial derivative of our product like this. So we're going to combine these two terms to form the partial derivative of this expression, and then we're going to omit these two terms when we write the final expression. Okay, so again, what I've done here is I have combined these two terms together to give us this expression, and then I've simply copied this here, this one here, this one here, and I have omitted these two because of the contraction. All right, so now let's look at the result. This final result is exactly what we'd get if we took the covariant derivative of this expression directly. We'd walk our way, we'd first of all take the partial derivative of the expression, which is this. Then we'd walk our way through each of the free indexes. Remember, we can skip the dummy indexes. So we'd start with index J, and here we have a contraction of index J. And then we'd go to index R, and here we have a contraction of index R. It's positive because it's an upper index. Then we have index S, and there's a contraction here. So the result you see here is precisely what we'd get if we just took the covariant derivative directly. And since we derived that through all of these steps, that proves our conjecture that this expression results in this expression. You get exactly the same result if we apply the product rule. So that example should convince you that the product rule works for tensors of any rank. The final property we want to look at is the commutative property. So we ask this question. Suppose we have a tensor, tk, such as this, and we have the occasion to take the covariant derivative of it with respect to two different variables. Well, the question is, does it matter whether we take it with respect to j first, then I, or if we take it with respect to I first, and then j. So it's this equation that we want to analyze. Now the first question here is, are we dealing with a tensor equation? Well, the answer to that is yes, because when we take the covariant derivative of a tensor, we always get a tensor. So this is going to be a tensor. Well, now we're taking the covariant derivative again of a tensor, so the final result is going to be a tensor. The same is true over here. And of course, the difference of two tensors with the same index structure is also a tensor. So we are dealing with a tensor equation. Well, now, let's look at what happens when we evaluate this result using Cartesian coordinates. Here we would have S, K, I, J, and of course in Cartesian coordinates the covariant derivative is just the partial derivative. So we'd start by taking the partial derivative of tk with respect to zj, then we'd take the partial derivative of that with respect to zi. So each of these is just the partial derivative. Now here we'd start first with the partial derivative of tk with respect to zi, and then we'd take the partial derivative of that result with respect to zj. And of course, doing that is just what we call the second partial derivative. So here we've got the second partial of tk taken first with respect to zj, then with respect to zi, and the second term is the second partial derivative of tk taken first with respect to zi this time, and then with respect to zj. Well, of course, you know that the order of differentiation in this case does not matter. The result of each of these two operations will be identical, so this expression is going to be equal to 0 in Cartesian coordinates. Now we can make use of the power of tensor calculus, and that is this. Since we know we started with a tensor equation, and we derived a tensor relationship in an individual coordinate system, we know that that tensor relationship is true for all coordinate systems. In other words, this expression will always be equal to 0 no matter what coordinate system we choose to use. Thus we say that the covariant derivative is commutative. The order of taking the covariant derivatives does not matter. Now it's often represented this way as an operator. We would write it down as the covariant derivative of I, then the covariant derivative of j, minus the covariant derivative of j, then the covariant derivative of I, treating this as an operator and applying it to a tensor out here. And we'd say that that's equal to 0. Now our choice of tensor here was quite arbitrary. I hope you see that regardless of what tensor you plug in up here, the analysis is going to be the same, whether it's a contravariant tensor, covariant, rank 1, rank 2, whatever. The choice of tensor does not make any difference. What we're going to find is that the result is always going to be 0. And that speaks to the nature of this operator itself. In other words, it is a property of the covariant derivative operation that it commutes. Now at first glance it may seem like the commutative property is somewhat mundane and unimportant. But by way of foreshadowing, I need to tell you that the commutative property is not always true. It is always true when we're dealing with Euclidean space. It's also true when we're dealing with any space that is characterized as being flat. But we're going to discover later on that when we're dealing with manifolds that are not flat, the commutative property does not exist. It's going to yield a non-zero result. So we're going to come back to this later and delve into it in much more detail when we talk about non-Euclidean spaces. For now, just be aware of the fact that in a Euclidean manifold, the covariant derivative is a commutative operation. Now what we did in this video was to explore three very important properties of the covariant derivative. The first is what we call the sum rule. And the sum rule is this, that the covariant derivative of a sum of tensors is going to be equal to the sum of the covariant derivatives of each of those tensors in turn. Now, because we can also factor out the scalar factors at the same time, that means that the covariant derivative is a linear operation. And I think it's also reasonably obvious to see that this works for subtraction as well. And it also works if we have more than two tensors. If we had three tensors added together, then on the right-hand side we'd have the sum of three covariant derivatives, and so it goes with any number of terms. Okay, the second thing we did was to take a closer look at the product rule. Now, video 34 was entirely devoted to the product rule, but it was limited to components of rank 1 only. We only looked at vector components in that video. The point of what we did here was to show that the product rule works also for tensors of any rank. So here I've got a tensor of rank 2 multiplied by a tensor of rank 3, and because they're multiplied together, this is going to be equal to the covariant derivative of the first times the second tensor plus the first tensor times the covariant derivative of the second. It works for any rank tensor. Now, this rule is also expandable. You can work it out on your own. You can see that if we had more than two factors here, say we had three factors, then we're going to have three terms on this side. We'll take the covariant derivative of each tensor in turn, once here, and once in the third term, leaving the other two as they are. And so the product rule will work for any number of factors, realizing that for each factor we're going to have a separate term added together on the right-hand side. And the final property we looked at was that of commutativity. And that's this. If we're going to take the covariant derivative of some tensor, first with respect to one variable and then with respect to another, we ask the question, does it make any difference what order we take these covariant derivatives in? And the answer is no. If we take the covariant derivative of our tensor first with respect to j, then with respect to I, we'll get the same answer if we take the covariant derivative with respect to I first, then with j. Now, I was very careful to point out that this property is only true for flat manifolds. For example, Euclidean space. Euclidean manifolds are flat, so it works for Euclidean manifolds. There are other manifolds for which it works as well, but they're all flat. Once you get to a manifold that is curved, then this property does not exist. You'll get a non-zero value for this operation if the space is curved. So we're going to return back to this property later as we begin to look at non-Euclidean spaces. And we'll spend a lot of time there because this is a key topic in that study. And finally, let me make a couple of comments that apply to all of these properties. The first is this, that as a matter of convenience, I've used specific examples, but please understand that all of these properties work for tensors of any rank or index structure. And secondly, I expect that you recognize each of these properties as being applicable to the simple operation of the partial derivative. The partial derivative satisfies the sum rule, product rule, and commutativity. Now, we pointed out a number of times that the covariant derivative can be thought of as a generalized partial derivative. It applies not only to affine coordinates, but it also applies to curvilinear coordinates. So what we've really shown here is that the properties that you already know and understand about partial derivatives carry over and apply equally well to the covariant derivative. Now in the next video, we're going to introduce a property that is unique to the covariant derivative, and that's the metronylic property.